So in this video, I'll be going over the exam 4 study guide I made for you guys. Okay, so let's start on 1A. It asks, which types of bonds are on the central atom mixed to form hybrid orbitals in the following? So for 1A, it's bromine trichloride. So for this, you want to start off by doing the Lewis dot structure of this. So it's Br, Cl, Cl, Cl. Bromine is the central atom because it's the least electronegative of these two atoms present. So you guys should know how to do Lewis dot structure by now, I hope. So I'll just go through like real quick and do it for you guys. So with this 24 electrons are used, but if you add up the total valence electrons from these four, you get 28. Since bromine has 7, chlorine has 7 as well. There's 3 chlorines, add up the 7 from this one, you get 28. So since you just used up 24 right here, there's still 4 more electrons, and those go around the bromine, giving it an expanded valence shell. So when it asks um, uh, which types of bonds, it refers to sigma, pi, and lone pairs, the ones that are around the central atom. So from these bonds, we want to figure out what like combination of sp3d2 forms around the central atom. So you see there's 1, 2, 3 sigma bonds. No pi bonds since there isn't double bonds here and stuff. And 2 lone pairs right here. 1, 2. So it's 2 lone pairs. So altogether, these form sp3d1. Oh, and this is what you're looking for. So you want to box this right here. Now for B, it's let's separate this real quick. It's Cl2O. So oxygen's the central atom is the least electronegative, and it's got 3 chlorines surrounding it. So in total 6 plus 14 is 20 electrons we gotta work with. So I'll do that real quick for you guys. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's good. See, each atom has an octet. So now we want to look at um the stuff around the centrum, uh, around oxygen. So you see there's 1, 2 sigma bonds. That's kind of ugly. Hold on. 2 sigma bonds. 2 lone pairs. 1, 2. So add those up. That's sp3. That'll be your answer. Just zoom out to get those. All right. So number 2 asks, chromium adopts the body standard cubic unit in its crystal structure. If the density of chromium is 7.14 grams per centimeters cubed, find its atomic radius. So for that one, we can't really solve for radius right off the bat using the density, which means we want to like build up to that, you know. So we're gonna be using the A equals 4 radius over the square root of 3, and the volume equals length cubed equations. So I got this from the body standard cubic unit structure. Since that's what chromium adopts, you know. So for body-centered cubic unit structures, BCC, it has 2 atoms in the structure in total. So we want to start with this. So with this, uh, we convert it into number of moles. So 1 mole of chromium, we use Avogadro's number, 6.022 times 10 to the 23rd chromium atoms. My handwriting's a little ugly, but yeah. So from this, we go to a mass, using chromium's molar mass, which is 52.00 grams chromium for every 1 mole of chromium. Okay, so from this mass, we can now use the density, which is 7.14 grams per centimeter cubed, to convert into a volume. See, a volume right here. So it's 7.14 grams of chromium. Put that there too. For every 1 centimeter cubed. Yeah, and that gives us a volume. What I got was 2.42 times 10 to the negative 23rd centimeters cubed. So with this volume, we're going to solve for a length. So we rearrange that to solve for length equals this the cube root of your volume. See this. So plugging that in, length equals the cube root of 2.42 times 10 to the negative 23rd centimeters cubed. Like so. Let me fix that real quick. Boom. Yeah. So that gave me 2.89 times 10 to the negative 8 centimeters. So this is our edge length. Remember, since we're working with a cubic unit structure, it's a cube, which means all the lengths are the same. So this is our edge length, A. This one. So to solve for radius, we just rearrange this equation to solve for R. So it would be R equals A times the square root of 3 divided by 4. So just plug those in. R equals 2.89 times 10 to the negative 8 centimeters times the square root of 3 divided by 4. And that got me a radius of 1.25 times 10 to negative 8 centimeters. That'll be your answer right there. Okay, so for number 3, it asks, which substance has the higher boiling point? Explain your decision. So with these, whatever it asks, like, which has the higher boiling point, uh, which has the greater like dipole moment or like greater surface tension, you want to think of like intermolecular forces and differences in electronegativity. You know, like which 2 atoms are farther apart? Because the farther you are on the periodic table, like in most cases, the greater electronegativity like difference you have. So for A, it's sodium bromide or phosphorus. I think it's tribromide or just bromide. I don't think it really matters, but so between sodium and bromide. Sodium is a metal. Um, Bromide is a nonmetal, which means the bond they form is ionic. Um, Here for phosphorus tribromide or bromide, I don't know. Um, it's just a covalent bond, like dipole induced stuff like that, which means they're closest to each other, so they won't have like as big a as big a difference in electronegativity as sodium bromide, which means this is a stronger bond. They would have the greater boiling point. So it'd be um on your exam, you should like circle it and be like for your reason, be like stronger intermolecular forces, intermolecular forces, or like greater difference in um electronegativity, En, right here. So these should be your answers for that stuff. Circle or box, doesn't really matter which one you do. Um, Circle or box your answer and state why. Wait. For B, it's water, H2O, or HBr. I think it's hydrobromic acid. I think. Oh, let's look at this. Um, Hydrogen is bonded to oxygen. Which bond does that make? Well, I can only like wait for you to answer it, so I'll say it myself. It's a hydrogen bond. It's one of the strongest bonds, like in terms of intermolecular forces. So when hydrogen is bonded to either oxygen, nitrogen, or fluorine, it makes a hydrogen bond. So this is a hydrogen bond. This isn't a hydrogen bond. It's just a covalent bond. I think it's a dipole-dipole, I'm pretty sure. So it's dipole-dipole, which isn't um as strong as a hydrogen bond, which means this would be our choice between which has the higher boiling point. And for your reason, just be like, same as this basically, like stronger intermolecular forces. I'm not gonna spell that out, but intermolecular forces, or put like, yeah, it's a pretty good answer. I feel like Schultz would accept this, or I hope, and you could put like H bond or something like that. Yeah. So for these, you just like look at like where they are in the periodic table to see like how great the difference in electronegativity is, or you have to like think back to like the intermolecular forces present, like what is it? Dipole dipole, ion induced dipole, um ionic bond. I think it's just ion induced dipole. Hydrogen bond, non-dispersion forces, stuff like that. I'm not gonna name all of those because I can't like remember them off the top of my head, to be honest. But yeah. So number four is just the same as number three basically, but here it asks for which of the two molecules has a greater dipole moment. Again, we gotta explain why. So, um, like three, you're just looking at which bonds are present, basically. So, or I mean, which uh types of intermolecular forces are present within the molecules. So for A, it's CH3. Sorry, CH3, CH3. It's got a name probably, but I'm not gonna like try like I'm not gonna try to pronounce that, bro, or try to like say it. So CH3, CH3, or magnesium chloride. So magnesium chloride, metal, non-metal. These are what is ionic bonds. CH3, it's a pretty common case of just London dispersion forces, which are the weakest forces. The dispersion. So between London dispersion, the weakest force, and ionic bonds, pretty strong forces. Which ones have greater dipole moment? Um, um, it had to be magnesium chloride because, like I said, it's an ionic bond, and these have the weakest forces. So for this, you could just like box your answer, and for your explanation, just be like um greater difference in electronegativity. Um or you could word it as like greater change in electronegativity. That's delta. So greater delta En or greater difference in electronegativity. The same thing basically. Okay, so for B, it's between sulfur dioxide or phosphoric acid, H3PO4. So if we look at the like Lewis dot structures, it's PO4 with the H's being attached to three of these O's right here. Okay, so looking at this, what do you guys notice? What bond is this? This is a hydrogen bond, which means there's hydrogen bonds present in this one. But what about sulfur dioxide? There is no hydrogen bonds present, which means this would have stronger intermolecular forces. Therefore, um, a greater dipole moment. Also, because sulfur and oxygen are pretty close to each other in the periodic table, which means the difference in um, electronegativity wouldn't be that great compared to H now. So it'd be phosphoric acid as the answer, and you could put same as this, be like greater difference in electronegativity, or you could put like um stronger intermolecular forces, like so. I would go with this one though, since it asked for dipole moments, not like stronger bonds and stuff. That's it. Okay, so number 5 says draw the molecular orbital diagram and find the bond order of O2 plus. Write the outer valence electron configuration and state whether it's stable and paramagnetic. So MO diagrams are these right here. I'll just draw it out for you guys. It'll take a while. It's these big drawings you guys should remember seeing, like from I think chapter 10. Yeah, it's kind of crooked, but I don't really mind this. So you guys might have noticed that this right here is pointing down because we're working with oxygen. Which means there's no mixing involved. So, mixing is involved if we're working with boron, carbon, or nitrogen. Um, if we work, if we were working with these, then this little pyramid thing would be pointing up instead, like this. But since we're not, it's pointing down. So these two boxes are called pi orbitals. Single box is sigma. So um what I like to say is you can't have pi without bacon, you know? You can't have pi on the bottom, this pi orbital, without boron, carbon, or nitrogen, bacon. Let's see, look at this. So now we're just gonna go through and label everything. Next to the orbital, we put 2p or 2s, since these are the period numbers, or I mean, the orbitals were oxygen is on, you know. So this is sigma 2s, sigma star 2s. The star is reserved for the ones that are on like up the top half of the orbital diagram. So this is on the top half. It's sigma par, sigma star. I mean. So this is sigma 2p, pi 2p, pi star 2p, and sigma star 2p. Okay. So now we start off by filling each side here with the valence electrons of the molecule. So oxygen has 6 valence electrons. With 2 of them, there's 12 in total. But since we have a positive 1 charge, we take 1 away from here. So it'd be 11 in total. So these 11 we're gonna split up into these sides right here. One's gonna be odd. Doesn't really matter which side it is. So just like just pick one. So 11 split up. We'll have one side with 6. Oh, sorry. We start off by filling up the bottom ones first. So it's 1, 2, 3, 4, 5, 6 electrons. 7, 8, 9, 10, 11. See, 11 electrons spread out between these two sides right here. Okay, so now we're gonna start filling in these orbitals. Think of like filling a glass of water with water from both sides, you know? So these electrons are the sides. We're filling up this glass from bottom to top. So we start off at the very bottom, sigma 2s. So each box can hold 2 electrons. So we siphon 1 from each side. 1, 2. There's 2 left over from this side, so 3, 4. That's good. Now we use these electrons to fill in these boxes right here. So it's 1, 2, 3, 4, 5, 6. We have 2, 4, 6, 7. So the last one, 7, is right here. So this should be a complete molecular orbital diagram. So for the outer valence electron configuration, think of that as like a regular like electron configuration, but using these orbitals instead. So remember, like here, I'll try it out. A normal electron configuration is something like 1s2, 2s2, 2p6, 3s2, stuff like that. We're gonna place these numbers and letters with these things right here. So we start from bottom to top. So the first one is sigma 2s. That one has 2 electrons in it. So we put 2. Then sigma star 2s. That one's also got 2 electrons. Now we go to sigma 2p. Sigma 2p. That one's got 2 electrons as well. Now it's pi 2p right here. That one's got 4 electrons. So it's pi 2p 4. Now we go up here to pi star 2p. It's only got 1. Pi star 2p is 1. We don't include the sigma star 2p because there are no electrons in this one. And that should be a valid outer valence electron configuration there. So now we want to state whether it's stable and paramagnetic. So to find whether it's stable, we want to look at bond order. So remember, bond order is 1/2 of the sum of bonding electrons minus anti-bonding electrons. So what I mean by bonding and anti-bonding, oh, bonding electrons are the ones that are on the lower half of this orbital diagram. So the ones from the sigma 2s, sigma 2p, and pi 2p. Basically, the ones that don't have this star next to them. The ones with the star next to them are anti-bonding. Okay. So the bond order for this one is 1/2 of the bonding electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 minus anti-bonding, which is 1, 2, 3. 8 minus 3 is 5. So 1/2 of 5 is 2.5. Sorry. 2.5. So a bonding order that's I think greater than 0 is stable. So since the bonding order here is greater than 0, that means it's stable. So we put stable. Either um bonding order has to be greater than 0 or greater than 1. I think it's 0, but you guys can check me on that. So now to see whether it's paramagnetic. So paramagnetic means there's electrons that aren't bonded in the valence electron stuff right here. And diamagnetic means everything is fully bonded. So if you see here on our 2p orbitals, there's electrons that aren't bonded like this fully, which means this is paramagnetic. So just write down paramagnetic. It would be diamagnetic if all of these were filled. Like this. But they're not, which means it's diamagnetic, or it's paramagnetic. That should be it for number 5. Okay, so 6 asks, show how the atomic orbitals around the central atom lead to the hybrid orbitals it adopts using partial orbital diagrams. So what that means is we have to use the, what is it? The S, P, and D orbitals up to show how, like, 1, 2, 3, yeah, to show how the central atom reaches its sp3d2 combination. Okay, so for the first one is germanium chloride, GeCl4. We start off by drawing the um, Lewis dot structure. So germanium with 4 Cls around it. Germanium has 4 valence electrons. Chlorine has 7. So add those up, you get 32 valence electrons you can work with. So we're just gonna fill everything in. And this should be a good or valid Lewis dot structure. So the bonds around this the central atom germanium are 4 sigma bonds. Okay. So, or in other words, there's 2, 4, 6, 8 electrons around it, which means we do um for these orbitals, want to fill them up. We want to fill them up to the point where 4 orbitals are fully filled. So it's pretty easy for this first one. It's um, 1s orbital and 3p orbitals can all hold 8 electrons. So this makes sp3. That is how you show partial orbital diagrams. And this makes sense because there's 4 sigma bonds around the center atom, right? Those add up to sp3 as well. See? So you want to show it like this for your exam. I'm pretty sure. Yeah. Okay. Now B. B is phosphorus pentafluoride. So there's 5 fluorines around 1 phosphorus. So each fluorine has 7 valence electrons. Phosphorus has 5. So 7 times 5 is 35. Plus 5 from phosphorus, we're working with 40 valence electrons. Right? 7, 14, 21, 28. Yeah. So 40 valence electrons. So we start off by filling, or by making each atom reach an octet. This is kind of like the boring part, but you have to show like the full Lewis dot structure to get points. So it's 8, 16, 24, 32, 40. See? We use up all 40 electrons. Now we want to count the electrons around phosphorus. There's 2, 4, 6, 8, 10 electrons around phosphorus, which means we want to fill up 5 orbitals, or want to fully fill up 5 orbitals. So that means we get 1 s orbital because there's always just 1 s orbital, 3 p orbitals, and 1 d orbital. See, it's 2, 4, 6, 8, 10. So this adds up to be sp3d1, which can be like proven by looking at the bonds around phosphorus. There's 1, 2, 3, 4, 5 sigma bonds. They make sp3d1. And that's it for number 6. This is what Schultz means by partial orbital diagrams. You want to show that these orbitals add up to the sp3d2 combination. One thing I forgot to point out is you have to label like the orbitals here with the correct period number for the center atom you're working with. Like for phosphorus, it's in period 3, which means you use 3s, 3p, and 3d. Germanium is in period 4, which means you use 4s and 4p orbitals, like so. Okay, so 7s, calculate the heat absorbed by water when 2.500 kilograms, starting at the melting point, reaches a temperature of 117 degrees Celsius. On my copy, it's like that for the kilograms. That's just a spelling error. It's supposed to be kilograms, not kg. But yeah. So for 7, this is kind of like a unique problem, since like if you remember how Schultz like explain it, you think of it like this, each plateau is a change in phase. So if we're thinking of like water, like from this problem, water goes from ice. Here it melts. Here you're heating up the water. Here the water boils. And here you're heating up the steam. So think of it like this. When you reach a plateau, um, let me see. A plateau basically means a change in phase. So a change in phase. For those, you use the equation heat is number of moles times the heat of fusion or vaporization, whichever one you're at. If you're here from ice to water, you're melting ice, which means you use heat of fusion. If you're going from water to steam, you do vaporization, whichever one you're working with. So here in um these slope lines, this is just like heating up a solid, liquid, or gas. So heating up is your standard Q equals N C delta T, huh? N C delta T like that. Is usually M C delta T, but here we're working with moles instead. So since we're working with moles, we want to convert the 2.5000 kilograms of water into the number of moles of water. We start off with that. So 2.500 kilograms of water. Convert that to the number of grams. Then from there, you use the molar mass to convert into the number of moles. So I think it's 18.05 grams of water for, oh, sorry, wrong side. 1 mole is 18.015 grams of water. And that should give us 138.773 moles of water. But since we're working with 4 sig figs, just round that to 138.8 moles. Okay. So since since in the problem we're starting at the melting point, we start at the Q equals N times heat of fusion or vaporization. So I'll do this in steps. So first step is going from solid to a liquid. It's a phase change. So use Q equals N times the heat of fusion. So plugging those numbers in, it's Q equals 138.8 moles times the heat of fusion, which is given to you, 6.02 times 10 to the, no, sorry, wrong one. 6.02 kilojoules per mole. So you see, the moles comes out, you'll be given an answer in kilojoules. Now we're at a liquid, we want to heat it up into, we want to heat it up to a point where it's boiling, which means we're going from 0 degrees Celsius up until 100 degrees Celsius. I got the 0 degrees Celsius um uh from the point of where like ice turns into a liquid or like a liquid turns into ice. So uh, we use Q equals N C delta T plug those in. Q equals 138.8 moles. Um, um, the specific heat capacity of water is 75.4 joules over moles times degrees Celsius, and that's times the change in temperature, which is final minus initial. So final is 100 degrees Celsius, since we're getting to the boiling point, minus 0 degrees Celsius, just 100 then. And that should give us an answer in joules. So now the third step is we're heating up the liquid, or we're in the phase change from a liquid to a gas. So we use this equation again. But instead of using the heat of fusion, we use the heat of vaporization. So we just plug those in. The heat of vaporization is 40.7 kilojoules per mole. That should give us an answer in kilojoules. Now the final step is we heat up the gas from 100 degrees Celsius up until 117 degrees Celsius. So again, we're using the Q equals N C delta T. So it's Q equals number of moles, 38.8 moles. Specific heat capacity of the gas is 33.1 joules over moles times degrees Celsius. Times change in temperature. So our final temperature is 117 degrees Celsius minus our initial, which is 100 degrees Celsius. That should give us an answer in joules. So doing all the math, I found number of joules, joules. Add those up to find the total heat absorbed by water when 2.500 kilograms. Starting at the melting point is raised to a temperature of 117 degrees Celsius. It's a pretty big number, but you're rigging with a lot of water, so yep, that should be it for this problem. Okay, so 8 says rank the following in terms of decreasing surface tension, and to explain your ranking. So for this one, it's kind of the same as the previous two, the dipole or the dipole moments and boiling point. You want to look at like what forces are present within the molecules. So there's three molecules: CH3OH, um, CH3, CH3, and H2CO. So it says in terms of decreasing surface tension, so we start off with the one with the highest surface tension first and work our way down. So in other words, we want to start off with the molecule that has the strongest um, um intermolecular forces present. So in this one right here, CH3OH, we have a hydrogen bond present. In CH3, CH3, we only have Lund dispersion forces. Dispersion. And in H2CO, we have dipole-dipole forces. So, which of these three forces do you guys think is the strongest? You can't really answer me, so I'll say it for you guys. But it's this one. This is the strongest, since hydrogen bonds are like really strong. Um, uh, don't ask me why, but dipole dipole are second strongest. At the bottom are limited dispersion forces. They're always going to be the weakest ones. So these are like the guaranteed like last place. So we start off in terms of decreasing. So strongest one first. So it's C H3OH. Um H2CO, and finally CH3 CH3. So you just want to look at what forces are present in these molecules. Um, um and rank them accordingly. If it says decreasing like this problem, you start off with the highest or the strongest force ones and work your way down. And if it asks for increasing surface tension, you want to start off with the molecule with the strongest surface or the strongest intermolecular forces first, and work your way up. That's about it for number 8. Okay, so for number 9, it asks, draw the Lewis dot structures and resonance forms of the following. So let's start off with the first one. It's sulfite, SO3 minus 2. So we start off by drawing the Lewis dot structures, like it said. So S with 3 O's around it. Both sulfur and oxygen have 6 valence electrons. So 6 times 4 is 24, plus the 2 electrons for the negative 2 charge means we're working with 26 electrons. So we fill in each outer electron with 8 electrons. Yeah, to reach an octet. And we should be done, right? But no. Let's look at former charges. So it's 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1 for all of these. And this is 1, 2, 3, 4, 5 plus charge. So even though the charges add up to be negative 2, we don't want each atom to have its own former charge. We want to minimize how many atoms in the molecule have a former charge. So instead of that, we draw it like this: sulfur, double bond, single bond, and we fill everything in. And here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The last 2 electrons go on top of here, giving sulfur an expanded valence shell. So now let's look at former charges. Oxygen has 0 former charge since 1, 2, 3, 4, 5, 6. This one has a negative 1. So does this one. But this sulfur has 0 former charge. 1, 2, 3, 4, 5, 6. 0. To find former charge, let's see. In case you guys don't remember, it's your atom's number of valence electrons minus the sum of lines. So sorry, lines. Like this right here, lines, or like in other words, bonds. Plus each dot around it, or just electrons. So like for oxygen right here, there's 1, 2, 3, 4, 4 dots, 2 lines. Oxygen itself has 6 valence electrons, so 6 minus 6 is 0. Same here. Sulfur 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. That's how we found, or I found, the former charge. Okay. Anyways, yeah. This is the valid, or one of the valid resonance structures for SO3 sulfite. So, let's see, not this. So now we want to solve or find all of the other possible resonance structures. This is pretty easy. Just look at where you can change like stuff, but still like keep the same molecule. Like the double bond, for example, you can change the double bond to be from um this right oxygen to be here this bottom oxygen. So like so. Oops, sorry. Like this. This is another possible resonance structure. Now you can change the double bond to be here on this left one instead. And remember to completely uh, create each Lewis dot structure. Sorry, okay, forgot this. Yeah, boom. So all three of these are the possible resonance structures for sulfite SO3. So you're gonna do this, but I just boxed it for you guys. Okay. Okay. So for B, we're working with bromine trioxide, BrO3 minus. I feel like that has a name, but um I don't want to think about it too much. So, we start off by drawing the Lewis dot structure again. So bromine with three oxygens attached to it. We fill in each outer electron with eight, or outer atom, my bad, with eight electrons. And boom, we used all 26 electrons. But like A, we don't want like each atom to have a formal charge. We want the least amount of atoms in the molecule to have a formal charge, which is why we don't do this. We do this instead. Now each, or now both oxygens right here have. Oops, sorry. Both oxygens here have a zero formal charge, and this bromine right here has a zero charge as well, which means this oxygen right here will be the only one with a -1 charge. See, since BrO3 minus only has one negative charge, um, we want one negative formal charge right here, or we want um, the charge to add up to be -1. So like A, we could change the double bonds here, um, to create new resonance structures. So instead of being here, we could put it right here instead. Kind of drawing these like kind of crooked, but like that, or I could draw it like this. Either way, you want to like show where the negative charges are, or any charges for that matter. Boom. Sorry, it's a little like crooked, but But that's how you draw the resonance structures for these two molecules. Okay, so number 10 asks, determine the ideal bond angles for each molecule center atom and state where you should expect to see deviations. So what it means by deviations, like in my opinion, is like where like the geometry isn't like how it's supposed to be. Like if you see that the last page on a study guide for the Vesper stuff, you see it's like all single bonds, you know. Um, you don't see any double bonds there. But here, like for this molecule, for example, you do see a double bond, and that's where you should expect to see some deviation, like right here. So for uh, this carbon atom, what's it called? The shape is going to be trigonoplanar, which means the bonds are or the ideal bond angles are going to be 120 degrees. But you should see deviations at the double bond. Double bond right there. And for this nitrogen atom, it's good like this for the double bond because it's like um and for this nitrogen here, you should expect to see deviations on the lone pair. Since its shape is bent, you wouldn't see a deviation here in the double bond like you did for carbon. So the bonds should be less than 120 degrees and deviations at the lone pair. Same with this oxygen. So it's tetrahedral with two double bonds or with two lone pairs. So the angles are less than 109 degrees. And deviations are seen at the two lone pairs. So for B, it's CH3 O CH3 again. Okay, so let's start with the oxygen. So the oxygen, like the one in the last problem, you should see deviations at around the two lone pairs. And like the one from the last problem from A, its angles are less than 109 degrees. I found these angles by just looking at the table. If I didn't say that already, just look at the table. See, there's four groups around oxygen, so you go down to number 4 right there in the table. There's two lone pairs of those four groups, so you go across to the to the two lone pairs. See, it's bent right there, bent or angular. People call it bent mostly, but yeah. So deviations at two lone pairs. So for the carbon, it might seem normal, but the oxygen here is pulling stronger than the hydrogens around it. Since these bonds are non-polar, this is polar. That means it's pulling stronger on it. So you'd see deviations here around the oxygen atom for this carbon. So it's tetrahedral. So the bond angles would be 109 degrees. And you should expect to see deviations at around the oxygen atom. So basically, wherever like the normal shape is like disrupted. See, this is disrupted by the oxygen atom, and the oxygen atom is disrupted by the lone pairs around it. You know, that's kind of like how I see it, to be honest. Okay. Last question. Number 11 says methane has a boiling point of negative 164 degrees Celsius at 1 atmosphere and the vapor pressure of 42.8 atmospheres at negative 100 degrees Celsius. What is its heat of vaporization? Okay, so for this one, we're going to be using the Clapeyron equation, which is let me see, it's the natural log of P2 over P1 equals negative heat of vaporization over R um, times the inverse change in temperature. So 1 over T2 minus over T1. Okay, so to solve for heat of vaporization, we want to rearrange this whole equation to just solve for this. So we want to start off by, let me see, multiplying this by R. So it'd be ln P2 over P1. Sorry, P1 times R. And dividing both sides by the inverse change in temperature. So it'd be like this. And that'd give us just negative heat of vaporization. We want to get rid of the negative, so just divide both sides by -1, basically. Since it's if you think about it, it's -1 times the heat of vaporization. So this would be multiplied. We divide both sides by -1. Either way, it'll uh, it'll get rid of this negative and bring it over to this side. So it's heat of vaporization equals negative all of this. Um, 1 over T2 minus 1 over T1. So now let's look for our variables. Doesn't really matter which ones we choose, to be honest, but our P1 is 1 atmosphere. Our T1 is negative 164 degrees Celsius. We convert that to Kelvin, and our P2 is 42.8 atmospheres, and our T2 is negative 100 degrees Celsius. So we convert that um to Kelvin. It's 173. Just add 273 to each of these Celsius numbers. Into this one, it's 109 degrees Kelvin, or just Kelvin, you know. So now we plug everything in. Oh, we gotta say, but our R is 8.314 joules over moles times degrees Kelvin. So with this, you plug everything into this equation. So it'd be heat of vaporization equals, let me see, negative natural log of P2, which is 42.8 atmospheres, over P1, which is just 1 atmosphere, times R, which is 8.314 joules over moles times Kelvin, divided by 1 over T2, which is 173 Kelvin, minus 1 over T1, which is 109 Kelvin. So that should give us an answer of 90 9,200 joules per mole. Doesn't ask what unit it's supposed to be, so you could do either joules or kilojoules. Doesn't really matter. But this should be it for the study guide. If you guys have any questions, just let me know down below in the comments. I know this isn't the best video since like it's my first video ever doing something like this, but if you have any feedback, just let me know, I guess. And uh, that should be it. Good luck, guys. I won't be here for the exam, but I will be present in the study-a-thon. So I'll see you guys then. If you guys decide to show up. And yep, that should be it. Have a good weekend, guys.